T3.2. An AP Stats student designs an experiment to see whether today's high school students are becoming too calculator dependent. She prepares 2 quizzes, both of which contain 40 questions that are best done using paper and pencil methods. A random sample of 30 students participates in the experiment. Each student takes both quizzes, one with a calculator and one without, in a random order. To analyze the data, the student constructs a scatter plot that displays a linear association between the number of correct answers with and without a calculator for the 30 students. A least squares regression yields the equation predicted calculator score equals negative 1.2 plus 0.865 times the pencil score, correlation 0.79. Which of the following statements is or are true? Okay, so statement number 1. Okay. If the student had used calculator as the explanatory variable, the correlation would remain the same. All right, so what statement 1 essentially boils down to is this. If we graph x versus y, or if we graph y versus x, right, does that change the correlation? Yeah. So I don't think this is something we explored too deeply in class, but it's something that you can check really quickly with software. So I've gone to Staplet and I've created 2 variables. The x variable is the values 1 through 5, and the y variable is the square of those values 1 through 25. Okay. So I'm going to do an analysis of this. All right, you can see that it kind of has a quadratic form to it because we're looking at the squared values. But look at the correlation, okay? 0.981. Okay. Now, what I've done on the next tab is I've switched the variables. So I put the squared values in first as the explanatory, and the values 1 through 5 as the response. Okay. All right, you can see that this has a concave down shape to it, yet the correlation is still 0.981. Okay, so pretty interesting property about correlation is that it doesn't matter which variable you choose for x and which one you choose as y, switching them does not affect the correlation. Okay, so for this statement, the correlation would remain the same. That is true. All right, statement number 2. If the student had used calculator as the explanatory variable, the slope of the least squares regression line would stay the same. Right, so the first statement was about whether the correlation would stay the same. This next statement is about whether the slope would stay the same. All right, let's go back to Staplet and we'll compare these 2 tabs. So here is where we had x versus y, and we can take a look at the equation here, and the slope is 6. Okay. Now we'll switch over to the other tab where we graphed y versus x. Take a look at the equation there. And the slope is not 6. It's actually 0.16. Okay? So they do not produce the same slope. All right, so that statement is false. Okay. Now, why would the correlation stay the same but the slope change? Well, kind of a simple answer is that the correlation is a unitless number, right? There's no units attached to correlation. But slope has units, right? Slope is the change in y versus the change in x. Okay? So if you're graphing y versus x, that's what the slope represents. When you're graphing x versus y, now the slope represents something different. It's the change in x versus the change in y. Okay? So because slope has units, it makes sense why changing the role of the variables would affect the value of the slope. All right, the third statement says that the standard deviation of the number of correct answers on the paper pencil quizzes was smaller than the standard deviation on the calculator quizzes. Okay, so pencil paper was the explanatory variable. Maybe I should write that underneath. And explanatory. And the calculator scores were the response variable. Okay. The correlation is 0.79 and our slope is 0.865. Okay. Now, there is a formula and this is on the formula sheet, that the slope of the least squares regression line is equal to the correlation times the ratio of the standard deviations, and the ratio is set up as sy over sx. Okay. Now, we don't know either of these standard deviations, so we can't plug those in, but we know the slope, and we know the correlation, so we can at least plug those numbers in, right? So the slope is 0.865, and the correlation is 0.79 times this mystery ratio, sy over sx. Okay. Now, in order for the left side to be equal to the right side, right, in other words, for this equation to be true, the entire right side must equal 0.865, which means that this ratio here has to be bigger than 1, right? Because I already have a number that's smaller than this, so I have got to multiply it by something bigger than 1 to increase the overall value there, right? Or, I mean, if you just want to carry out the calculations, right, we could simply divide both sides of this equation by 0.79, right, and to isolate the ratio itself. So sy over sx is equal to, now look, this ratio over here is bigger than 1 because the numerator is bigger than the denominator. Okay, so I'm just going to write, I won't even simplify it, 0.865 over 0.79, and we know that that is greater than 1. Okay, so then that means that this numerator must be bigger than that denominator. So sy must be greater than sx. Okay, now y was calculator, so the standard deviation for the calculator scores must be greater than the standard deviation for the paper pencil scores. All right, let's see how that aligns with the statement itself. The standard deviation of the number of correct answers on the paper pencil quiz was smaller than the standard deviation on the calculator quiz. Yes, pencil was smaller than calculator. So that is a true statement. So going through the answer choices, it's going to be D, right? Only statements 1 and 3 are correct.